Good morning, my dear students. Let us start the class. See, in yesterday's class, I just started with the module 5, where we started with the concept of dynamic programming. So, in that class, we discussed just introduction to the dynamic programming. We defined what is the multi-stage decision process, and also we have discussed a few examples where we can consider the process as a multi-stage decision process. And also, I think we have discussed the representation of the multi-stage decision process with different elements of the decision process by just considering the single stage decision process, and we have discussed various elements, just like an input state variable or output state variable, the decision variable, and the return functions. Okay. So in today's class, let us continue with the same things where I left in the last class. So just I will recall the things what we discussed in the last class. So multi-stage decision process is the one in which number of single-stage processes are connected in series, so that the output of one stage is the input of the succeeding stage. This is a definition what we made in the last class for multi-stage decision. Okay, and also we have discussed a few examples for which how we can consider or how we can take the process as a multi-stage decision process. Okay, and also I think we have discussed the representation of multi-stage decision process, just writing the single-stage decision process in the form of a rectangular block, and also we have the different parameters in the form of input parameters s or decision variables x, and certain output parameters t, and also the return or an objective function r. So this is what we were discussing in yesterday's class, and also we just discussed these functions, and also I think at the end I think I will stop at this point where the multi-stage decision process. You can see the number of stages here, stage n to stage 1, and correspondingly we have an inputs and output. Corresponding outputs we have discussed. We can see in this block diagram. Okay, right? So I think I discussed these things in the last class. So this is the one equation what I supposed to end in the last. So in today's class, let us just continue with the same thing here. Generally, what happens? The systems, what we generally going to get it in a real life problems is a non-serial system. So when you want to use the dynamic programming technique to optimize such kind of non-serial systems, it is necessary for us to convert that system into a serial system. In the sense, non-serial systems needs to be converted into a serial system, so that we can use the dynamic programming approach or a dynamic programming technique to optimize such type of system. Okay. So how we can do that? We will take one simple example, and we will go into discuss how non-serial systems will be converted into a serial system. Okay. So a serial system is the one whose components are connected in such a way that the component of one is the component of one of any component is the input to the succeeding component. The output of one component will be the input to the succeeding component, and that is what we generally call it as a serial system. Okay. So now let us take one simple example, which is in the form of a steam power plant. Okay. So let us discuss what are the main parts of main elements of a steam power plant, and how initially it is non-serial, and how we can convert that into a serial system, so that we can apply the dynamic programming problem for such kind of problem. Okay. So let us take the example of a steam power plant, so which is shown in the figure A. See, this is the figure A. So here the components of this steam power plant consists of a pump, feed water heater, boiler, superheater, steam turbine, and electric generator. This is the steam power plant what we are having. So here, when we look at this, uh, the system, the steam power plant here. So there is some amount of heat will be taken out by the steam turbine to heat the feed water once it is being pumped. Once it needs to be pumped to the boiler. In the sense, some amount of heat energy will be used to heat the feed water in the feed water. So this will form a non-serial system. Okay, so we can see this figure A. So we are showing this is the different elements of a steam power plant here. And in the figure B, you can see I have just blocked this. So I just closed this pods, feed water, heater, boiler, superheater, and steam turbine. So why? Because this will represents the non-serial system. So where some amount of heat will be taken from the steam turbine to heat the feed water. So then this will constitute the non-serial system. So everything looks like a serial. If you don't have any heat taken from the steam turbine to heat water, then it will form a serial system. But generally, see the amount of heat, the some amount of heat, what we are going to take, that is especially the 1/3 of the heat what it steam turbine will generate, will be used for heating the water before it is being fed to the boiler. Okay, so this will constitute. So this will what we call it as a loop. Okay, the loop is like this. So it is a loop like this. It will be keep on like this. So therefore, this will forms the non-serial system. So therefore, this non-serial system needs to be converted into a serial system. So what we do here is, so instead of that, we will going to consider everything. So look at the figure number C, serializing a non-serial system here. Serializing a non-serial system here. So we are going to take the entire, the 4 different elements, just like a feed water heater, boiler, superheater, and steam turbine. Everything will be considered as a single element. Single element. This is what we have written here. The non-serial system can be equivalent serial system by regrouping the components so that loop is redefined as a single element as shown in the figure B and C. In the sense, the entire the elements of all the 4 elements have been grouped together to form a single block. Okay, so this will be in series with the 2 other components. One is a pump, another one is a electric generator. So what we are doing here is, so any system, if you find it is a non-serial system, just like a simply if you have any loop or a feedback, something if you are finding from one element to the another one element, so that will constituting the non-serial system. So in such systems, what we do, all the systems within that recycling from first to the end, what you are having, everything will be grouped together as a single element. Okay, and this will be in series with that of the first and the last element. Then that will go to constitute the serial system. So once you get a serial system, then it is easy for us to use the dynamic programming approach and you can optimize the system. This is how we can convert the non-serial system into a serial system. Okay, this is one simple example what I have taken for discussing how we can convert these non-serial systems into a serial system. Correct? Next, we move on to the most important thing, what we call it as the types of multi-stage decision problem. So, this serial stage, multi-stage decision problems are classified into 3 categories. One is called an initial value problem. Second one is called final value problem. And third one is called boundary value problem. Okay, so let us discuss each one because each problem has its own importance and significance, and we should be in a position to know, and we should be in a position to decide whether the problem is an initial value problem or a final value problem or a boundary value. So because we will going to get a system and we will going to convert the system if it is a non-serial into a serial system, and later onwards based upon the inputs, based upon the function what we will going to generate. So we will going to decide whether based upon the inputs input or the data what it is available for us. So we will going to decide whether the problem can be treated as an initial value problem or a final value problem or a boundary value. So then how do we conclude or how do we decide the system is the problem is initial value or final value or boundary? So this is what we will go to discuss it. Okay. Let us start with the first one, the initial value problem. So when do we say the problem is, or when do we consider or when do we treat the problem as initial value problem is if the value of the initial state variable, if the value of the initial state variable, it is Sn plus 1, is prescribed, the problem is called an initial value. In the sense, so if you have any problem whose the initial state variable, the very first, the input variable or the initial state variable, what you will go to give. This is what in the block, what we can block diagram, what we are showing here. See, this is the end stage multi-stage decision process here, end stage. Okay, the last one is the end stage. Okay, and the first one is the first stage. So it is just like a in the reverse order. Okay, so for the end stage process, so here the input state variable, the initial state variable, we can say initial state variable, this is called initial state variable. The process will be continuing in this direction. Okay, so initial state variable, so Sn plus 1. So S corresponds to an initial state variable or input state variable or data, anything you can take it as. So input state variable Sn plus 1 is prescribed. Prescribed this, the value of this will be having a constant value. You cannot change the value or you cannot vary the value of initial state variable. If the value of the initial state variable is prescribed, okay, then we can treat that problem or then we can call that problem as an initial value problem. Please remember this. Okay, this is the continuation. So Sn plus 1 is the input to the stage n, whereas Sn is the output of the stage n, but it should be the input to the next succeeding stage, which is an n minus 1. Okay, the output of n minus 1 is Sn minus 1. Like that, you will have an n number of stages. Okay, so in between we have got Si plus 1 is the stage, is ith stage. Ith stage, the input state variable is Si plus 1, whereas the output is Si. And similarly, for the first stage, the input state variable is S2, whereas the output state variable is S1. So like this is what we call it as the initial value problem. See, the representation of prescribed value. So you can see here the vertical line what I am showing here. Okay, so this vertical line against the direction of the input state variable or a direction in which the variable has been input to the system. So if this line will represents the prescribing the value is prescribed means we are going to represent it by drawing a perpendicular line against to the arrow what it is showing for the input state. So this, please remember, this is why this right line what I have shown. See, you can see here in the previous example, I have not shown this. Okay, so we cannot consider whether it is a final value or initial value or boundary value. But in this problem, what I have shown here, when we consider or when we say the input state variable is prescribed, okay, so then the representation, graphical, pictorial representation is you have to put the perpendicular line. You have to draw a perpendicular line to the arrow what it is being shown. So that represents the input state variable is being prescribed. Okay, and we will go to treat such kind of problems as a initial value. Right? Next, we move on to the second one, the final value problem. So it is just like If the value of the final state variable S1 is prescribed, the problem is called final value. Notice that the final value problem can be transformed into the initial value problem by reversing the direction of SI. We can reverse the direction of SI, I is equal to 1 to n plus 1. So when you reverse the direction, then the problem will become, we can convert. Okay, that we are going to see later. Let's first understand what you mean by initial value problem. So if the final state variable, so in this problem, look at here, Sn plus 1 is the initial state variable, whereas S1 is the final state variable. If you prescribe the final state variable, then the problem is called final value problem. Final value problem. So you can see the representation here. So in this process, S1 is the final state variable, and since that value of the final state variable is prescribed, okay, so that representation is by just drawing the perpendicular line to the arrow what it is shown. So this will indicate that the final state variable, the value of the final state variable is described. Okay, so when the value of the final state variable is described, then we have to treat this problem as the final value problem. And he says that this final value problem can be transformed into the initial value problem by reversing the direction of SI. Instead of reversing, if you just reverse the direction of S1, so if everything goes in this direction, then it will become the initial value problem, how we discussed in the previous slide. Okay. Then comes the last type of multi-decision problem is a boundary value problem. In this type of problem, if both the values of input and output variables are specified or prescribed, the problem is called boundary value. So, in the case of a boundary value problem, both the input state variable, the initial state variable, as well as the final state variable, or we can put it as input variable, input state variable, and the output state variables of a process or of a problem is being prescribed or specified, then the problem is called the boundary value problem. In the sense, in such type of problems, what happens, you will be knowing what is the value of the input variable and what is the value of the output variable. So in the sense, they will be giving this range. So in such cases, that problem we are going to have, we have to treat that as a boundary value. So this is what the representation, what we can show here is across the input variable. The input variable to this system is Sn plus 1. So you can see this line, perpendicular line. So that is representing the value of Sn plus 1 is prescribed. Okay, as we move towards the end, the output, the S1, the output of this system S1. So here also we have drawn the perpendicular line, so which will representing the value of S1 is prescribed. This output state variable. If both input and output state variables are prescribed, then we have to consider or we have to treat such type of problems as a boundary value. Please remember, this is how we will go into categorize the multi-decision problems, and also, so when you are in the problems, if you be careful, look at this line. So where this line has been given, or sometimes in the problem statement, you have to decide whether we have to treat this as an initial value or a final value or a boundary value. So when you want to treat that, so you have to write this block diagram and we have to show. So whether you are solving the problem as the initial value, final value, or boundary value by just indicating or just representing this perpendicular line against the state variable. Okay, these are the three important types of multi-stage decision problem. Next comes the concept of sub-optimization and principle of optimality. Till now, what we discussed is what is multi-decision problem and how we can convert a non-serial systems into a serial system, and also we have discussed the different types of multi-stage decision. But of course, these are all the preliminary things what we will go into have before we just use the concept of dynamic programming. But when it comes for the actual application of dynamic programming, the two important things. One is called sub-optimization and the optimality, the principle of optimality. So these two important concepts are used for the application of dynamic programming problem or to solve any problems by using dynamic programming techniques. Okay. Let us discuss what is this sub-optimization, and we are going to have the statement of principle of optimality. And later, we will going to have the procedure. We have one procedure to use the dynamic programming problems that we will going to discuss later. Okay. So let's start with now. A dynamic programming problem can be stated as follows. So the statement of any dynamic programming problem, so this is what we were discussing. Find x1, x2 to xn, which optimizes, where x1, x2 to xn represents the decision variable, are called decision variable. So the ultimate objective or ultimate goal of dynamic programming problem is to find out the optimum value of the decision variable. This is x1, x2, x3. Then we can say the problem is get optimized. So the which optimizes the function. So the objective function is given here, f, which is ri. Ri is the return function, okay, which is equal to. So these equations we already been used, and we already written these equations in the previous slides, so that you can understand here. So this is the function. This is the function, the objective function, for which we will go into optimize. So which is the function of the input variable and the decision variable. Whereas R corresponds to the return function, okay, which satisfies the design equation. Which satisfies the design equation, that is input variable is the function of. This also we have discussed in the previous slide. So this is what the dynamic programming problem statement is. Always when you look at any dynamic programming problem, so the format, the model will be in this way. Okay. So now the dynamic programming makes use of the concept of sub-optimization and the problem of optimality in principle of optimality in solving this problem. In the sense, so what we have shown in the two equations above, that represents the dynamic programming problem. Okay, and to solve the dynamic programming problem, so we have to make use of the concept of sub-optimization and the principle of optimality. Okay, so now let us discuss this. What is the sub-optimization and principle of optimality with the one simple example. Okay, so let us take the example, and I will go to explain what is this sub-optimization concept, and finally we will go into state the principle of optimality. Okay. So let us take the example here. So here, in this case, we are having the example which is in the form of a water tank. Okay. The statement will be like this. Explain the concept of sub-optimization in the context of the design of a water tank as shown in the figure below. The tank is required to have a capacity of 1 lakh liters of water and is to be designed for the minimum cost. So this is not the water tank figure here. So I think you can just imagine the water tank. Okay, so which will be constructed for storing the water. So maybe you might have seen very huge water tanks will be constructed so it can store the gallons of water, right? So basic, the three important parts of water tank. One is the tank which stores the water. Okay, the tank is being supported by the columns. Okay, which in turn, the columns which in turn will be resting on the foundation which has been made beneath the ground. So three important things. Because why I'm talking only three important things here is they are the load carrying members. Okay, all the load will be transferred from tank to the columns and which in turn is transferred to the foundation. Okay, so here we have to the what is the requirement here is the tank has to store a water of 1 lakh liters. 1 lakh liters of water that needs to be stored. Yeah, 1 lakh liters of water that needs to be stored and it is to be designed for the minimum cost. So these two important things. The two requirements are 1 lakh liters of water to be stored and second one is we have to design it for the minimum cost. So just imagine, I have not shown the picture of the water tank here. I hope everybody has seen the water tank and you just imagine here. So I've just modeled it for solving, which can be suited for our multi-stage decision problems or dynamic programming. Okay. So how we have modeled here, the block diagrams, what we have shown, it is showing the multi-stage decision problem here. So where the tank is the first element. Okay, so you can see the stage tank, column, and then we have a foundation. Okay, so we'll take tank as an I, J as a column, and foundation as a K. Okay, so correspondingly, the decision variable for tank will be Xi, for column it will be Xj, and for foundation is X suffix K. Okay, so here, so what will be the input state variables? What is the input to the tank? Is the main thing is the weight of the water. Weight of the water is the main thing for the tank. So because tank will store the water and the weight of that, because we are designing it for the minimum cost. So when it comes to the cost, the material cost, the manufacturing, construction cost, labor cost, there are so many concepts will come into the cost. So everything will correspond to the cost over here. Okay. So here.
Wait. Oh my God.
So here, what we are doing is the weight of the water will be the input to the tank. Okay. So then output of the tank will be weight of the water plus tank, which in turn is the input to the columns. Okay. Then here. So weight of the water plus tank and column is to the foundation. I think one thing is missing here. So the input to the foundation will be weight of the water plus tank plus column. So it will should come over here. Okay. Then output of the foundation is weight of the water plus tank plus column plus foundation. So this is what we are constituting it as the multi-stage decision problem. The one input I am just missed here. So the weight of the water, see, just add the weight of the water and tank is the input to the columns. And moving on to this, weight of the water plus tank plus column. So that will be the input to the columns over here. Okay. So here, why I am talking about here is, so when what decisions you will going to make, that will reflect in the form of a return function, which is nothing but the cost. So decisions are very important here. What kind of decisions you will going to make? Okay, that will matters a lot here. So whatever the decisions you will going to make, that will be returned in the form of a cost for us. So that is what the return function is nothing but it is the effectiveness of the decisions what you will going to make. Okay, so therefore here Ri corresponds to the return function for the tank, Rj is the return function for the column, whereas Rk is the return function for the cost function or return function for the foundation. So this is the actual diagram of a actual model of the water tank carrying a water. Okay. Now, what we do here is the main objective, the main ultimate objective is we need to design it for two things. One is for the required capacity of 1 lakh liters, and second one is for the minimum cost. So now, when you start optimizing this, optimization is very important, or when you want to minimize the cost. So you should be very careful. So where we supposed to start? Starting in the sense, see what happens basically, we are decomposed. See, this entire water tank has been decomposed into 3 parts: tank, column, and a foundation. Now the question is where to start, whether we need to start from optimizing the tank, or we need to optimize from the column, or we have to optimize from the foundation. So we need to have to proceed with some logical sequence, because logical sequence in the sense, so we should know where to start and where to end. Simple example. So if I don't follow the procedure, and if I just vaguely, if I start optimizing the columns over here, the column is the intermediate element between the tank and the foundation. So basically, what is columns required? Columns require the steels, that is reinforcements, and the concrete. So if I choose a steel, steel is the expensive in the columns. Okay. So if I choose the steel which is of less cost, because my ultimate aim is to reduce the cost. So if I choose the steel of lower cost, of course, so you are optimizing the columns. But what happens to the succeeding element, foundation? So when the columns or when the steels are of low capacity or low cost, then ultimately it has to, that foundation has to withstand the columns as well as the tank as well as the water. So then you need to have a very huge foundation, very huge foundation. So when you have a huge foundation, then you cannot reduce the cost of the foundation. You cannot optimize the cost of the foundation. All right, I'm following what I'm talking about. So if you just vaguely, if I start optimizing the columns, I want to say, so steel, I want to reduce the cost of the steel. If I start, and if I consider, if I just choose the steel of less cost, and if I just design, and that will give a load on the foundation. The foundation has to be very huge, then we cannot optimize the cost, or we cannot optimize the foundation, or we cannot minimize the cost of the foundation. So this is the one biggest problem if you don't move it in the logical sense or logical procedure. So therefore, what we generally start here is we're going to start from the bottom element, and we will going to move to the top one. So this is the procedure what we generally adopt in our dynamic programming problem. Always we're going to start with the one which we're going to take the complete load, and we're going to proceed to the next one, and we're going to proceed to the top one. In the sense, what I'm talking about here is, so we need to start optimizing the foundation first. When you optimize the foundation, then similarly, we can, of course, relevantly, we can move to the columns, and then we can move to the tank. This is how we generally follow the logical procedure in getting a solution for the optimization problem, right? So this is the diagram what we have shown here. So you see here. So this is the actual diagram. Okay, so we will go to treat this as an initial value problem only. See, because we will be knowing how much amount of water, because 1 lakh water needs to be stored. So this is the input state variable is, we know, because it is a 1 lakh liters of water. So this is the line what we are showing here. It is the line which represents the initial value prop. Okay. So now we'll start optimizing. We are optimizing, sub-optimizing the component I. So I've just taken it as in the reverse way over here. So please remember here. So initially, previously I have taken I as a tank and J as a column and K as a foundation. But we had to start from the bottom one. I have taken I as a foundation here. I've just reversed the notations here. Component I. The component I is foundation, component J is columns, and component K is a tank. So what we start here is, I will start optimizing the foundation, because foundation will carry the weight of a water, weight of a tank, and weight of the columns. So all the three elements weight that will be transmitted or will be withstand by the foundation. If I start optimizing the foundation, so it will leads to the optimization of the components. So how we will going to do? Let us see. So first we are going to optimize the sub-optimization of the component I. This is the first step what we will going to do. So whatever the necessary things you have to do, you will go into optimize how much amount of size, what should the thickness of the foundation is supposed to have. So everything by calculation, everything you can do, you can optimize the foundation I. In the second step, what we do, we group both the component I and component J. We group, subgroup. See, we are initially it was only the component I was sub-optimized. In the second step, what we are doing is we are grouping the component I and component J together. We are grouping component I and component J together, and we will go into sub-optimize this. We sub-optimize this together. Okay, so then, so these two components we will going to get sub-optimized. And in the last stage, what we do, we take all the three components, including component I, component J, and component K, that is foundation, columns, and tank, and we will go into optimize these components. This is what we call it as the sub-optimization. Okay, so optimizing each sub-optimization of each component, and finally it leads to the optimization of the entire system. Okay, so therefore, since the sub-optimization are to be done in the reverse order, the components of the system are also numbered in the same manner for convenience. Okay, so let us just stop with the defining the statement of principle of optimality. The process of sub-optimization was stated by Bellman as a principle of optimality. What does it state? An optimal policy has the property that whatever the initial state and initial decisions are, the remaining decisions must constitute the optimal policy with regard to the state of the resulting from the first decision. This is the statement of principle of optimality. Okay, so I will just discuss these things in the next class with much more details. Okay, so if you have any clarifications till now, you can ask, because only a few seconds left out for me. Anybody, any clarification, because dynamic programming and the sub-optimization are very important. Students, are you following? Any clarifications, any doubts? I'll continue in the next class. Sandesh?
Yes, sir.
Are you able to follow? The notion?
Yes, sir.
Okay, so if you have any clarification,